let's suppose you're on this square and it's blue, and so blue gives you a cost of 3.9. Well, actually, let me be consistent with my code. I'm just going to erase these because they mess up my flood fills. If this square happens to be blue, and that means the cost is 3.9, then I'm claiming the cost to get to here is 3.9. And that's too humongous. And the cost to get to here is 3.9, and the cost to get to here is 3.9, and the cost to get to here is 3.9. Does it matter if the cost depends on the square you're on or the square you're going to? It turns out it doesn't matter in the long run. So if you're zoomed up super close, yeah, it kind of looks like everything has the same cost, right? But once you get onto this square, well, this one's yellow, and this one's pink. And so if I go to the right, I'm going to get a different cost for my next move. And if I go to the left, I'm going to get a different cost for my next move. So as for the long run of the agent, it doesn't matter whether you count the pixel you're on or the pixel you're going to. In reality, you're spending about half the time on the pixel you're on and half the time on the pixel you're going to. So you could average between them if you wanted to. I just took the easy, lazy way, and I just said, the cost of all your actions depends only on the color you're on. And it turns out that works just fine, because you're never going just one pixel away. You're always going many pixels away. If you only go one pixel away, then that might get you into an ambiguous situation. Hey, maybe that's what's causing the ambiguity problem. I don't know. But just for your information, the way my code works is it only cares about the pixel that you're on. But now, what should be the cost of moving to this green square?
Well, it would be square root of 2 times 3.9.
Yeah, it should be square root of 2 times 3.9. Because the cost that it gives you, this 3.9, is the cost of moving 1 unit, right? And I'm not going 1 unit, I'm going root 2 units. So I need to manually increase the cost, or else it will falsely learn that the optimal path is to go like this. And it'll take a bunch of diagonal cuts because it gets more done with less cost, right? Okay, if you look closely at the paths I take, see that red line, and you see how
Do you put casting to an int when you're doing square root of 2? Like 3.9, stuff like that?
No, I'm doing my distances all in floating point arithmetic. But you see how my line is actually composed of straight lines and diagonal lines, or horizontal and vertical and diagonal lines? That's because I gave it 4 searching options. If you wanted to, you could break it into hexagonal regions and do hex paths, or you could discretize your potential steps into any number of things that you wanted. I'm just having you do 8 because it gives you the extra complexity of having to deal with this diagonal problem, which is good practice for making sure you're proficient with AI stuff. Any questions on that, or is this way more talking than was even necessary? I hope it was the latter. But it's okay to have questions. All right. So yes, you will need to scale every step by the distance it costs. One other thing I want to emphasize, the number that it returns based on the color of the pixel you're on, is that for moving 10 spaces or 1 pixel or what? I don't know, and it doesn't even matter. Here's why it doesn't matter. Because suppose this path costs 1 billion, and this path costs 100 million. Or wait, no. Suppose the path through the water costs 1 billion and the red path costs 100 million. Which one's better? Red one. Now suppose the yellow path costs 0.2 and the red path costs 0.02. Which one's better? Still the red path. You can scale your cost by any constant factor and it has no effect, right? It has no effect on what's optimal. Therefore, when you call get travel speed and it returns a number to you, you don't even need to know how far that number represents. It's just related to the color of the pixel you're on, and it's forgoing some amount of distance off of that pixel. And based on that, as long as you scale it by root 2 when you go diagonally, then your costs will all add up correctly. Okay. great. Then there's that. Back to the code. Okay, we went through the model. Let's look at the view really fast. My view extends JFrame, meaning that's what creates this frame-like window that makes it a graphical program. Okay? And it implements Action Listener, because this is what's called 50 times a second to keep redrawing the screen. Okay? So this is a bunch of JFrame stuff. Here, you can change the title of your window. You can change its size if you want. The JFrame has inside of it a panel. This panel is the big area of the window. So it's that big gray region inside of the window. And here's the code that draws the terrain inside of that panel. Oh, here's the code that draws all of the panel. And you see it draws the terrain, then it draws the sprites. Comfortable with the view? Any questions? Okay, good deal. You will need to touch slightly your controller. I have this mouse pressed event. I think you might. Oh, this just pumps it into a queue that I wrote. Oh, I made my own linked list for queue of mouse events. No, actually, you don't need to mess with the controller, I think. I think the agent's the only thing you need. Now we just need to talk about the difference between uniform cost search and A* search, and then I think you're all set on this assignment. Okay? Okay. I have provided for you this nice pseudocode. This is the pseudocode for uniform cost search, but if you look it up, you will find that uniform cost search and A* search differ by the teeniest, tiniest little tweak. The only difference is the heuristic you use. And the heuristic is that one of them needs to be sorted by the cost of the path so far, and one of them, A*, needs to be sorted by the cost of the path so far plus an underestimate of the distance remaining to the goal. Okay? How does one do that? Any ideas? Yeah. Okay, let me answer that question real fast. So this is you. You're an O. This is your goal. The shortest path from you to your goal is a straight line. So if you measured that distance and you multiplied it by the fastest piece of terrain on the map, let's suppose it happened to be the color yellow for some reason, then the speed associated with yellow multiplied by that distance would represent the lowest possible cost of getting to your destination without knowing what's between you and the destination, right? We're going to use that as our heuristic in A* search. In reality, there's going to be all kinds of colorful things in the way. And because of that, the actual cost of getting to the goal will cost a bit more because you actually have the lowest cost is actually going to be something like that. But as long as you underestimate, A* search will still work. Where do you find the cost of the least costly square in all of the terrain? Good question. Here's what you do is, the answer to the question is, when your program first starts, I recommend maybe in just the constructor of the agent or somewhere else, wherever you want to, put some code that's going to raster across the whole screen and measure the cost of every pixel on the map and find the minimum one, and then you'll know the lowest cost of any pixel on the map. And then if you multiply that by any distances, you'll always have a heuristic to use.
Okay.
The reason that's going to be efficient, I mean, obviously it's inefficient to visit everything in the map, right? Well, we're only doing that once, but we're searching hundreds and hundreds of times. So in the long run, that buys us time. And another thing I wanted to do that for is to emphasize that A* search really does depend on something that's always heuristic. There's no way to get an always reliable heuristic. You have to know something about the problem, In this case, the only way to know the problem is to visit every state, which is worse than the cost of the search itself. So A-star search really isn't a better algorithm. It's only better if you have some knowledge, some inside way to guess on what's a better path to the goal. The one thing I need to talk about is comparators. Did you guys use a comparator in assignment 1?
Yeah.
Okay, good. Did you understand your comparator in assignment 1?
I think I do.
Okay, well, often when I provide code, students use it and don't understand it. So here's my chance to force you to understand it a little better. You're going to need a comparator in this assignment. So go back and look at the comparator and understand what's going on. This assignment, you're going to need 2 comparators that are different. Here's why. You have both a set and a queue. So that's going to be, we have this queue here that I'm calling frontier and this set that I'm calling bin there. It's going to be very tempting for you to use the same comparator for both of them, right? Was anybody tempted by that in the first assignment that did that? I guess you didn't really need a comparator in your queue because you all used a plain old queue. But a priority queue needs a comparator. Here's a really big tip. Don't use the same comparator for your queue as your set. Why? Because your queue is supposed to be sorted by cost. Whereas your set, what happens if you sort by cost? Then you're saying anything that has the same cost as what you're doing, you've been there before. But that's the whole frontier, right? The whole frontier is not necessarily a place you've been. In fact, it's exactly where you haven't been. Well, you haven't been everywhere just beyond the frontier. So it'll really screw you up if you use the same comparator. You're going to have to use one that sorts your states by what they are, their x and y position, and that's the one I gave you an example for in assignment 1. And you're going to have to use a different comparator that sorts the states by how much they cost. And make sure that your sets and your queues are sorting by what they're supposed to sort by, otherwise you'll get very confused. As long as they're sorting by different things, then you should be good. Now, how do you sort one thing by 2 different criteria? Yeah, that's what comparators are for. Just use one comparator for your queue and one comparator for your set. A lot of people are using Java comparers. What's the difference between a comparer and a comparator? Yeah, a comparer lets the object itself decide how it's sorted, and a comparator lets the data structure sort it. You want the data structure to decide how it's sorted because the state doesn't know how it's to be compared. When the state is in the queue, it needs to be sorted by cost, and when the state is in the set, it needs to be sorted by position. Is that clear? Okay, well that's important, so if you get confused, make sure you revisit that concept and think about it for a while. That's all I got today. Thanks for coming.